Hello, I am Alkida Balliu, and in this video we will talk about the distributed edge coloring problem. In particular, we will see an algorithm that solves this problem in time quasi-polylogarithmic in delta. This is a joint work with Fabian Kuhn and Olivetti. Our setting is the classical local model of distributed computation, first formalized by Lineal in the late 80s. This is a synchronous message passing model where we do not restrict neither the size of the messages nor the computational power of each computing entity. Nodes have unique identifiers, and the time complexity is given by the number of communication rounds needed in order for each node to output its own part of the solution. Since we do not restrict the size of the messages, an algorithm that runs in t rounds in this model can be seen as a function that maps t-hop neighborhoods into outputs. Note that the t-hop neighborhoods of two neighboring nodes do not look very different, in the sense that the overlapping of the views is quite large. We could say that two neighboring nodes are mostly symmetric. On the other hand, in most of the problems of interest in the area, two neighboring nodes are asked to give different outputs while computing their output in parallel. Think about the vertex coloring problem, for example. This suggests that we want to achieve some sort of symmetry breaking between nodes. While randomness is very helpful in achieving this task, dealing with symmetry breaking is a major challenge in the deterministic distributed setting, which is the setting we will focus on in this presentation. In the theory of distributed computing, there are four classical symmetry breaking graph problems that have been in the center of attention since the 80s. These problems are maximal independent set, maximal matching, delta plus 1 vertex coloring, and 2 delta minus 1 edge coloring. While in the centralized setting all these problems can be trivially solved with greedy algorithms, in the distributed setting a lot of questions related to these problems still remain open. Essentially, we still do not know the exact time required to break symmetry. These four problems are related with each other. In fact, for example, 2 delta minus 1 edge coloring is a special case of delta plus 1 vertex coloring, as 2 delta minus 1 edge coloring is just a delta plus 1 vertex coloring on the line graph. Also, we know that if we have an algorithm for solving MIS, we can use it to solve vertex coloring. Thanks to various works, we have learned more. For example, we know that delta plus 1 vertex coloring can be solved much faster than MIS. Moreover, while nowadays we know the tight complexity as a function of delta for solving MIS, we still don't know the exact complexity of solving delta plus 1 vertex coloring. Over the years, there has been a lot of progress in understanding the complexity of these problems. A very recent breakthrough result from Rojan and Ghaffari shows that these problems can be solved in polylogan deterministic rounds. This result essentially says that these problems can be solved efficiently with deterministic algorithms, but we also know that in the case where the maximum degree of the graph is small, these problems can be solved much faster. In fact, for all of them, we have algorithms running in order of log star n plus some function of delta. Note that log star n is much more local than log n, since in the local model, in order of log n, we can see some global features of the graph. For example, in order of log n rounds, each node can see either a cycle closing or a node with degree at most 2. Hence, in order to understand how local these problems are, researchers have studied the complexities as a function of the maximum degree delta. So let's see what we know about the locality of these problems. Barenboim, Elkind, and Kuhn showed that delta plus 1 vertex coloring can be solved in order of delta plus log star n rounds, implying that also maximal independent set can be solved in the same number of rounds, by first finding a coloring and then greedily going through color classes. We know since the 80s that this dependency on n is necessary, as Lineal showed that even in very simple graph families like paths and cycles, MIS requires omega of log star n rounds. Since very recently, we know that also the dependency on delta is optimal. A result from last year shows that we need to spend linear in delta rounds if we want to be optimal as a function of n. For the maximal matching problem, Panconesi and Rizzi showed in 2001 that it can be solved in order of delta plus log star n rounds. Also, the lower bound for MIS that was mentioned before is actually obtained by proving a lower bound for maximal matching. This implies that, like the MIS problem, also maximal matching, which could have been a potentially easier problem, actually requires linear in delta rounds. While maximal matching and maximal independent set are equally hard, we know that the delta plus 1 vertex coloring problem is easier. In fact, Fregnon et al. Showed in 2016 that the delta plus 1 vertex coloring problem can be solved in roughly square root delta plus log star n rounds. While Ligna's lower bound says that this problem cannot be solved faster than log star as a function of n, we still do not know any lower bound as a function of delta, and this is a major open question in the field. Lastly, a very recent result by Kuhn shows that the 2 delta minus 1 edge coloring problem can be solved in 2 to the square root log delta plus log star n rounds, while the only lower bound that we know, also for this problem, is omega of log star n. In this work, we study the locality of the 2 delta minus 1 edge coloring problem, and we improve upon the result of Kuhn. But before going there, let's see an overview of the progress that led to the current understanding. Since an algorithm for vertex coloring directly implies an algorithm for edge coloring, many results present in the literature regarding the edge coloring problem are achieved as a corollary. In fact, since 2009, we know that 2 delta minus 1 edge coloring can be solved in time linear in delta plus log star of n, and this result was achieved by Barenboim and Elkin and independently by Kuhn. This result was later improved by Barenboim, obtaining an algorithm that runs in order of delta to the power of 3 over 4 plus log star of n. 1 year later, Fregnon, Heinrich, and Kozowski improved even further the complexity of this problem, showing an algorithm with a running time of roughly order of square root delta plus log star of n. Finally, some logarithmic in delta factors were later improved by Barenboim, Elkin, and Goldenberg, and this is the fastest known algorithm that works both for delta plus 1 vertex coloring and 2 delta minus 1 edge coloring. But for solely the edge coloring problem, there are actually better algorithms. For example, if we allow a larger palette, that is, we allow order of delta colors, Barenboim and Elkin show that this problem can be solved in order of delta to the power of epsilon plus log star of n rounds for any arbitrary positive constant epsilon. But very recently, Kuhn showed that even if we restrict the number of colors to delta minus 1, we can solve edge coloring in time sub-polynomial in delta. In this work, we make a step forward in understanding the complexity of the edge coloring problem, and we show that 2 delta minus 1 edge coloring can be solved in quasi-polylogarithmic in delta plus order of log star of n deterministic rounds in the local model. In order to show this result, we actually prove something stronger. we show that degree plus 1 least edge coloring can be solved in time quasi-polylogarithmic in delta. But let's see more closely what this problem is and what is its relation with the 2 delta minus 1 edge coloring problem. In the least edge coloring problem, each edge is given in input a list of colors from some color palette, and the goal is to color edges with a color in their list such that the resulting edge coloring is a proper one. In the degree plus 1 least edge coloring problem, each list given to each edge E has size at least degree of E plus 1, where with degree of an edge E, I mean the degree that it has in the line graph. Now it is easy to see that 2 delta minus 1 edge coloring is a special case of the degree plus 1 least edge coloring problem, where each edge is given in input the same list of 2 delta minus 1 colors. Since the maximum degree of the graph is delta, the maximum degree on the line graph is 2 delta minus 2, and this means that to each edge we give in input a list of at least 1 plus its degree many colors. Hence, an algorithm for degree plus 1 least edge coloring directly implies an algorithm for 2 delta minus 1 edge coloring. In the rest of the talk, we will see an overview of the high-level ideas for computing degree plus 1 least edge coloring in time quasi-polylogarithmic in delta plus order of log star of n. So our problem of interest is degree plus 1 least edge coloring. But in order to solve it, we will first consider a more relaxed variant of this problem, where the lists of colors are large. In particular, we consider variants where the list of colors must be of size at least beta times degree plus 1. Then we will see how we can relate these two problems. This parameter that controls how much larger the list should be compared to the degree is called slack. So specifically, we say that the degree plus 1 least edge coloring problem has slack 1, while the variant where the lists must be of size at least beta times degree plus 1 has slack beta. We now introduce the high-level idea of our algorithm. We call T beta C the time required to solve the least edge coloring problem with slack beta, where the color palette has size C. Similarly, T1C is the time required to solve the standard least edge coloring problem. We mainly prove two things. The first one is that if we want to solve the hard case where the slack is 1, we can decompose this problem and instead solve many instances with a larger slack. And having a larger slack helps in solving the problem faster because edges have many more choices. In particular, we show that if we have an algorithm that is only able to color the edges if the slack is at least beta, we can sequentially run it beta squared log delta times, and in this way solve the harder case where the slack is 1. Now, all we need to do is to show an algorithm that solves the easier edge coloring problem where the slack is beta. To do that, we prove that we can express T beta C as a function of the time required to solve instances with smaller slack, but that also have smaller palette size. If we now just pick the right parameters and we solve the recursion, we get our quasi-polylogarithmic in delta plus log star of n time for solving degree plus 1 least edge coloring, and hence 2 delta minus 1 edge coloring as a corollary. So let's start by showing how we can use an algorithm that only works for slack that is high to solve the slack 1 case. So suppose that we can solve fast enough a relaxed version of the least edge coloring problem where each list has size at least beta times degree plus 1 for some suitable large enough beta. In order to create this slack on the size of the lists, we reduce the degree of the graph computed with effective edge coloring. Then the idea is to solve many instances of the relaxed list edge coloring problem sequentially by going through color classes. So for example, this idea applied on the graph shown in the figure would look as follows. At first, we compute a defective edge coloring. In the example, we are using 3 colors. Then, consider the subgraph induced by the edges of color 1. Notice that we have a graph with much smaller degree, but the lists are the same as before. In this way, we have increased the slack, and we can apply the algorithm for solving list edge coloring with slack beta on these edges. In this way, we obtain a proper coloring of the edges of this graph, of this subgraph. Then we continue on the second color class. At first, each edge removes from its list the colors that are already used from its incident edges. And if the remaining list is large enough, the edges take part in the algorithm that solves the relaxed list edge coloring problem. In this way, we obtain a proper coloring of all the edges that have been processed until now. We then repeat this process on the edges of the third and last color class, and at the end we recurse on all the edges that could not be colored because their color list did reduce by too much. We can show that each time we reduce the degree of the graph where we recurse by a constant factor. Hence, in order of log delta rounds, we are left with a graph with constant maximum degree. And there we know how to color the edges with degree plus 1 colors in order of log star n rounds. By doing this, we are able to express the time for computing degree plus 1 list edge coloring as a function of the time to compute the defective edge coloring plus the time to go sequentially through colors and solve the relaxed list edge coloring problem plus the time to recurse. And by computing the time to do so, we get the relation between the two time complexities as shown in the formula. Now that we know what to do once we have an algorithm for the relaxed version of list edge coloring, let's actually see how to solve these edge coloring problems when the size of the list is large. The high-level idea is to split the color space into many independent color subspaces and assign a subspace to each edge. Then, each edge reduces its list of colors by taking the intersection of the list with the colors in the assigned color subspace. In this way, we divide our problem into many independent subproblems, as we can recurse on each graph induced by edges with the same assigned subspace independently. In other words, what happens is that on one hand we reduce the size of the color lists, and on the other hand we reduce the palette size, and hence the degree of the instances where we recurse. This suggests that the operation of assigning color subspaces to edges must be done carefully. We must make sure that the size of the lists does not reduce too much compared to the new degrees. In other words, we want to reduce the degree of the subgraphs as much as possible while keeping the size of the new list as large as possible. So, by carefully doing this operation, we show that the time required to assign the subspaces is log p times t1p. Think about p as something much smaller than the color space C. Then, by assigning the subspaces, the downside is that we lose something in the slack of the lists. So when we recurse, we have a worse slack parameter that is beta over polylog p. But this is still okay, because we gain in the palette size that reduced to c over p. Our main contribution lies in the way we assign subspaces. To do that, we consider each subspace as a color, and then we define multiple defective least edge coloring instances that we solve sequentially. By doing things carefully, we are able to assign subspaces to edges such that the number of neighboring edges with the same assigned subspace is not too high. So, putting things together, on one hand, we can express the time for solving degree plus 1 least edge coloring problem as a function of the time required for solving the relaxed least edge coloring problem. On the other hand, we can express the time for solving a least edge coloring with slack beta as a function of the time for solving a least edge coloring with smaller slack plus the time for solving degree plus 1 least edge coloring. This gives us a recursive formula that expresses an upper bound on the time required for solving degree plus 1 least edge coloring, and by solving the recursion, we get our result. To conclude, in this work, we make a step forward in understanding the complexity of the 2 delta minus 1 edge coloring problem, showing that it can be solved in quasi-polylogarithmic in delta plus order of log star n rounds. So, natural question is whether we can bring down the time complexity to polylog delta plus order of log star n. Another important open question regards the lower bound side. The only lower bound we have for 2 delta minus 1 edge coloring is known since the late 80s, and it is omega of log star of n. So any progress on this end would be very interesting. And as a concrete question, can we, for example, show that 2 delta minus 1 edge coloring cannot be solved in little o of log delta plus order of log star n rounds? Many thanks for watching. I hope you enjoyed this talk.